In today's design session, we are going to talk about chat system design. So let's dive in. I'm pretty sure if you're part of modern human society, then you would have used a chat system. It could be WhatsApp, Facebook Messenger, WeChat, Line, Google Hangout, Discord. So a chat app performs different functions for different people. It is extremely important to nail down the exact requirements. For example, you do not want to design a system that focuses on group chat when the interviewer has one-on-one chat in mind. Before discussing further, we should remind ourselves of the design discussion framework. So as a first step, we should establish the problem statement. Second, we should get alignment of the requirements. That could mean back of the envelope calculations, some napkin maths, some discussions on the design tenets, invariants, system correctness, and operational requirements, and also discuss what is in the scope and what is outside of the scope of the discussion. Then we should agree on the high-level design, and from there on, we could dive deeper into few components. If time permits, we should discuss about failure modes and also discuss operational readiness requirements. That could mean observability metrics, some experimentations, but security and durability aspects of the design. So let's dive in. So let's establish the design scope here. So for example, our chat system should support one-on-one and group chat. It should be on both platforms, mobile and web app. Let's say it supports 50 million DAU and group chat limit is around 100 people. As we already discussed, feature supported is one-on-one chat, group chat, let's say online indicator. The system only supports text messages, no attachments, no media files. Text length should be less than 100,000 characters long, and chat history, let's say we want to maintain forever. In the discussion, we are going to focus on designing a chat app like Facebook Messenger with an emphasis on the following features, which we have discussed before. Again, I'm repeating here. One-on-one chat with low delivery latency, a small group chat, max of 100 people, online presence, multiple device support, push notifications, and it's also important to agree on design scale. We'll design a system that supports 50 million DAU. DAU stands for daily active users. So now let's try to sketch out a high-level design. Now, to develop a high-quality design, we should have a basic knowledge of how clients and servers communicate. In a chat system, clients can be either mobile applications or web applications. Clients do not communicate directly with each other. Instead, each client connects to a chat service which supports all the features mentioned above. So for now, let us focus on the fundamental operations. The chat service must support the following actions. For example, receive messages from other clients, find the recipients of each message, and relay the message to the recipients. If a recipient is not online, hold the messages for that recipient to the server until she is online. So pictorially, you can see there's a sender which sends the message, there's a chat service which stores and relays the messages, and it goes to the receiver. Now, requests are initiated by the clients for most client-server applications. This is also true for the sender side of the chat applications. In the figure, when the sender sends a message to the receiver via chat service, it uses the time-tested HTTP protocol, which is the most common web protocol. In this scenario, the client opens the HTTP connection with the chat service and sends the message, informing the service to send the message to the receiver. The keep alive is efficient for this because the keep alive header allows the client to maintain a persistent connection with the chat service. It also reduces the number of TCP handshakes. HTTP is a fine option on the sender side, and many popular chat applications such as Facebook used HTTP initially to send messages. However, the receiver side is a bit more complicated. Since HTTP is client initiated, it is not trivial to send messages from the server. Over the years, many techniques are used to simulate a server initiated connection. For example, polling, long polling, and WebSockets. Now, let's discuss briefly all these three options: polling, long polling, and WebSockets. Now, polling, as shown in the figure here, polling is the technique that the client periodically asks the server if there are messages available. Depending on the polling frequency, polling could be costly. It could consume precious server resources to answer a question that offers no as an answer most of the time. So as you can see on the right hand side diagram, there's a client. It asks new messages, server says nope. Again asks new messages, nope. New messages, yes, return the new message. New messages, no, and the connection could be closed. Now, long polling. In long polling, a client holds the connection open until there are actually new messages available or a timeout threshold has been reached. Excuse me. Once the client receives new messages, it immediately sends another message to the server, restarting the process. Long polling has a few drawbacks though. Sender and receiver may not connect to the same chat server. HTTP servers excuse me, are usually stateless. If you use round robin for load balancing, the server that receives the message might not have a long polling connection with the client who receives the message. A server has no good way to tell if a client is disconnected. It is inefficient if a client does not that much. Long polling still makes periodic connections after timeouts. So on the right hand side diagram, we can see there's a client, it asks, is there a new message? Server waits for new message. Yes, it returns the new message. Then the connection is closed. Then again, after some time, client asks, are there new messages? Nope, timeout. Now let's get to WebSocket. A WebSocket connection is initiated by the client. It is bidirectional and persistent. It starts its life as a HTTP connection and could be upgraded via some well-defined handshake to a WebSocket connection. Through this persistent connection, a server could send updates to client. WebSocket connections generally work even if a firewall is in place. This is because they use port 80 or 443, which are also used by HTTP and HTTPS connections. Now again, in the right hand side diagram, we can see there's a client. It says get and then there's HTTP handshake, acknowledgement, and the bidirectional message channel is established. By using WebSocket for both sending and receiving, it simplifies the design and makes implementation of both client and server more straightforward. Since WebSocket connections are persistent, efficient connections management is critical on the server side. Now, WebSocket was chosen as the main communication protocol between the client and server for its bidirectional communication. It is important to note that everything else does not have to be WebSocket. In fact, most features like sign up, login, user profile, etc. of a chat application could use the traditional request response method over HTTP. Now let us drill in a bit and look at the high level components of the system. On the right hand side, you can see there's a user, it sends a request, there's a load balancer, there's a service discovery service, there's authentication service, group management, and user profile services. Now the only stateful service is the chat service. The service is stateful because each client maintains a persistent network connection to a chat server. In this service, a client normally does not switch to another chat server as long as the server is still available. Now the service discovery coordinates closely with the chat service to avoid server overloading. We'll also go in detail during the deep dive session. Now the client maintains a persistent WebSocket connection to a chat server for real-time messaging. Chat server facilitates message sending, receiving. Presence servers manage online, offline status. API servers handles everything including user sign up, login, change profile, etc. Notification server sends push notifications, and finally key value store is used to store chat history. When an offline user comes online, she'll see all her previous chat history. So in the diagram on the right, you can see user, there's a WebSocket, and then there's a typical HTTP connection. Now the WebSocket goes to the real-time service, which are chat servers and presence servers, which interact with the API servers. An API server interacts with the notification servers, and the persistent layer is a key value store here. Now key value stores could be used for the following reasons. Key value stores allow easy horizontal scaling. Key value stores provide very low latency to access data. Relational databases do not handle long tail of data well. When the indexes grow large, random access is expensive. Key value stores are adopted by other proven reliable chat applications. For example, both Facebook Messenger and Discord uses key value stores. Facebook Messenger uses HBase and Discord uses Cassandra, though as of today, whether they use these technologies or not, I don't know. Now, here's a high level schema for messages and group messages. Now, messages could contain message ID, message from, to, content, and created app. Group message could be a channel ID, message ID, user ID, content, and created app. The primary key is message ID, which helps to decide the message sequence. We cannot rely on created at to decide the message sequence because the two messages can be created at the same time. The composite primary key is channel ID, message ID. Now, channel and group presents the same meaning here. Channel ID is the partition key because all queries in a group operate in a channel. Now, how to generate message ID is an interesting topic worth exploring. Message ID carries the responsibility of ensuring the order of messages. To ascertain the order of messages, message ID must be satisfying two important requirements. It must be unique. The second is it should be sortable by time, meaning new rows have higher IDs than the old ones. How can we achieve those two guarantees? The first idea that comes to mind is the auto increment keyword in MySQL. However, NoSQL databases usually do not provide such features. The final approach is to use local sequences number generator. Local means IDs are only unique within a group. And then the reason why local IDs work is that maintaining message sequences with one-on-one channel or a group channel is sufficient. Now, let's look at service discovery. So, the primary role of service discovery is to recommend the best chat server for a client based on the criteria like geographical location, server capacity, etc. Apache Zookeeper is a popular open source solution for service discovery. It registers all the available chat servers and picks the best chat server for a client based on a predefined criteria. Now, on the right hand side, you can see from the diagram that there's a user A, it logs in, the login flow goes through the API servers, and there's a service discovery layer powered by Zookeeper, and on the right hand side there's a WebSocket which connects to a chat server. Now, if you go step by step here, user A tries to log in the app. The load balancer sends the login request to API servers. After the backend authenticates the server, service discovery finds the best chat server for user A. In this example, server 2 is chosen and server info is returned back to the user A. User A connects to the chat server 2 through the WebSocket. So, message flows. It is interesting to understand the end-to-end flow of a chat system. In this section, we'll explore one-on-one chat flow, message synchronization across multiple devices, and group chat flow. So, step 1, user A sends the chat message to chat server 1. Chat server 1 obtains a message ID from the ID generator. Chat server 1 sends the message to message sync queue. The message is stored in a key value store. User B is online. The message is forwarded to chat server 2 where user B is connected. If user B is offline, a push notification is sent for push notification servers. Chat server 2 forwards the message to user B, which is a persistent WebSocket connection between user B and chat server 2. Now, message synchronization across multiple devices. Many users have multiple devices. Now, we'll explain how to sync messages across multiple devices. The figure shows an example of message synchronization. For example, the user A has two devices, let's say a phone and laptop. When user A logs into the chat app with the phone, it establishes a WebSocket connection with the chat server 1. Similarly, there's a connection between the laptop and chat server 1. Each device maintains a variable called current max message ID, which keeps track of the latest message ID on the device. Messages that satisfy the following two conditions are considered as new messages. The recipient ID is equal to the currently logged in user ID. The message ID in the key value store is larger than the current message ID. With distinct current message ID on each device, message synchronization is easy. On each device can get a new message from the KV store. So hopefully, pictorially, this makes sense. This is user A, phone. It connects to chat server 1, gets persisted, and then the session for user A laptop and phone are active, and then user A laptops receive notification or message. Now, small group chat flow. Assume there are 3 members in the group, user A, B, and C. First, the message from user A is copied to each group member's message sync queue, one for user B and second for user C. You can think of the message sync queue as an inbox for a recipient. This design choice is good for small group chat because it simplifies message sync flow as each client only needs to check its own inbox to get the new messages. When the group number is small, storing a copy in each recipient inbox is not too expensive. Now, on the recipient side, the recipient can receive messages from multiple users. Each recipient has an inbox that is a message sync queue, which contains messages from different senders. So in the diagram, you can see A, chat server 1, B sends to chat server 2. There's a message sync queue for user C, which receives messages from A and B and delivers it to C. Now, online presence. An online presence indicator is an essential feature of many chat applications. Usually, you can see a green dot next to a user's profile picture or a username. This section explains what happens behind the scenes. In the high-level design, presence servers are responsible for managing online status and communicating with clients through WebSocket. There are a few flows that will trigger online status change. Let us examine each one of them. Now, user login. The user login workflow is explained in the service discovery section. After a WebSocket connection is built between the client and the real-time service, user A online status and last active timestamp are saved in the key value store. Presence indicator shows that user is online after she logs in. For example, here we have user A, WebSocket connection, presence servers, and key value store. The key value store persists the presence data. So user A has this data says online, last active, and there's certain timestamp over there. Now, design deep dive, we are going to talk about user logout. When a user logs out, it goes through the user logout flow as shown in the figure. The online status is changed to offline in the key value store. The presence indicator shows the user as offline, which is obvious. Now, user disconnection. Periodically, an online client sends a heartbeat event to presence servers. If presence servers receives a heartbeat event within a certain time, say X seconds from the client, user is considered as online, otherwise it is considered offline. In figure, the client sends a heartbeat event to the server every 5 seconds. After sending 3 heartbeat events, the client is disconnected and does not reconnect within, let's say, 30 seconds. The online status is changed to offline. So in the diagram, you can see there's a 5-second heartbeat stops, 30-second lapses, and it's considered offline. Now, how do users A friend know about the status changes? The figure explains how it works. So as in the figure, you can see there's a user A, there are presence servers, there are channels A to B, A to C, A to D, and each user subscribes to those channels, and the presence notification is sent to those channels, and the subscriptions kind of get their status. Now, presence servers use a publish subscribe model in which each friend pair maintains a channel. Where users A online status changes, it publishes the event to 3 channels A, B, A, C, A, D. Those 3 channels are subscribed by the user B, C, D respectively. Thus, it is easy for friends to get online status updates. The communication between the clients and servers through real-time WebSocket. Now, wrapping it up, here are the final thoughts. Now, we discuss a chat system architecture that supports both one-on-one chat and small group chat. WebSocket is used for real-time communications between the client and server. The chat system contains following components: chat server for real-time messaging, presence servers for managing online presence, push notification servers for sending push notifications, key value stores for chat history persistence, and API servers for other functionalities. Now, additional talking points could be, we could extend the chats app to support media files such as photos and videos. Media files are significantly larger text in size. Compression, cloud storage, thumbnails are interesting topics to talk about. End-to-end encryption. WhatsApp supports end-to-end encryption for messages. Only the sender and receiver can read messages. So we could talk about how to kind of enable that. Caching messages on the client side is effective to reduce the data transfer between client and server, improve load time. Slack built a geographically distributed network to cache users' data, channels, etc. for better load time. Error handling. The chat server error, this might be hundreds of thousands or even more persistent connections to a chat server. If a chat server goes offline, service discovery, for example, Zookeeper, will provide a new chat server for the clients to establish new connection with. Message resend mechanism. Retry and queuing are common techniques for resending messages. Here are some useful reference materials. Do find time to read 1 or 2 of them. They'll be super helpful. All right. Hope this discussion was useful. Have a nice day ahead. Like, subscribe, and comment for more such designs. Thank you.